every time you ask Apple's Siri a question or you book a weekend getaway on Airbnb or even just scroll through a massive timeline on Twitter, you are essentially triggering a logistical nightmare.
Oh, yeah. It really is.
Right, because we have this expectation of like frictionless magic. You tap a screen, the results appear instantly, and it feels like the internet just intrinsically knows how to handle our requests. But behind that illusion of the cloud is this chaotic war for resources inside massive data centers.
It is a staggering amount of hidden complexity.
Yeah.
I mean, when millions of those seemingly effortless requests hit a data center all at once, managing the physical servers, figuring out which machine handles which tiny piece of the puzzle without the entire system just crashing under the weight. It's honestly one of the hardest problems in computer science.
Yeah, and that chaotic back-end reality, that is our mission for this deep dive. We are going to explore the architecture that tamed that chaos, which is Apache Mesos. This was a revolutionary piece of software. It completely transformed how the world's biggest tech companies operate their infrastructure. But before we jump into the actual architecture of Mesos, we have to talk about the pre-Mesos world.
The Dark Ages.
Yeah, exactly. We need to understand the specific flavor of chaos this software was built to solve. So let's look back at the late 2000s. If a company wanted to run a massive data processing job using Apache Hadoop and simultaneously run a different type of job using a framework like MPI, which, handles complex mathematical supercomputing tasks, they couldn't just throw them onto the same group of servers.
No, not at all. They literally had to build two separate physical clusters of servers.
Wow.
Yeah, it was the era of static partitioning. You had siloed hardware that was dedicated to specific frameworks. And the problem with that approach is twofold. First, you end up duplicating massive amounts of raw data across different physical machines just so both of those separate frameworks can actually access it.
Right, which sounds expensive.
Oh, incredibly. And second, and perhaps more critically, your server utilization is just abysmal.
Okay, I was trying to visualize this static partitioning earlier, and it feels like having two entirely separate kitchens in a massive restaurant.
Okay, I like that.
Like, one kitchen is exclusively for baking, and the other is exclusively for frying. So if you suddenly get a ton of cake orders, your baking kitchen is completely maxed out, right? The ovens are full, the bakers are overwhelmed. But over in the frying kitchen, your fry cooks are just standing around doing absolutely nothing.
Nothing at all.
And because of the rules of the restaurant, they are strictly forbidden from crossing over to help bake.
Yeah, that captures the inefficiency perfectly. You have highly expensive, very power-hungry resources sitting idle, and they cannot be repurposed dynamically to meet a spike in demand.
Which is crazy for a multi-million-dollar data center.
Exactly. So researchers at UC Berkeley, Benjamin Heinemann, Andy Kanwinski, Modi Zaharia, and their colleagues, they recognized this massive bottleneck. They originally called their project Nexus, and they set out to break down those kitchen walls. The result was Mesos. And what stands out immediately in their foundational research is that they achieved this initial vision in just 10,000 lines of C++ code.
Wait, really? That sounds shockingly small for a program designed to run an entire data center.
I know, right? But the small footprint was entirely by design. Mesos was built to be an incredibly thin layer. You can think of it as a single unified operating system for the data center.
Okay.
Instead of a human operator seeing 10,000 individual servers with static roles, Mesos pools all of those resources together. Every CPU, every gigabyte of RAM, every disk, it all becomes part of one massive shared environment. In the early UC Berkeley emulations, this thin layer successfully scaled to manage 50,000 emulated nodes.
Okay, let's unpack this. Pooling 50,000 computers together sounds great as a concept, but to run a unified system at that massive scale, there has to be a very clear chain of command. Like if I'm writing an application and I need to execute some code, how does the system actually manage the hardware?
Right. So that brings us to the fundamental architecture, which is the master and agent roles. In the Mesos ecosystem, the hierarchy relies on lightweight background programs, which are called daemons, and they're running constantly. The foundation of this is the agent daemons. An agent runs on every single physical server or node within the cluster.
Okay, so what is the day-to-day job of that agent daemon?
Its primary function is simply to report up the chain of command. It acts as a sort of inventory checker for its specific machine. So an agent on server A will constantly report, I currently have 4 CPUs and 4 gigabytes of RAM free. It just advertises its available capacity.
So it's the fry cook from our restaurant analogy constantly yelling out, hey, I have 2 empty fryers available right now.
That's the exact mechanism.
Yeah.
Now, all of those availability reports from tens of thousands of agents are sent up to the master daemon. The master collects this massive stream of data, and it acts as the central resource pool manager. It maintains a real-time view of the entire cluster's available inventory.
I have to challenge that design, though.
Okay, go for it.
If one single master daemon is collecting reports from 50,000 servers and then turning around and trying to schedule every single task for every single application running in a massive company, isn't that going to create a catastrophic bottleneck? Like, how does one master micromanage all of that without just freezing up?
Well, the short answer is it doesn't.
Oh.
Yeah, and that realization is exactly why traditional centralized schedulers failed at this scale. The core innovation of Mesos is that the master avoids micromanagement entirely. It does not dictate how applications should do their jobs. Instead, it relies on a modular allocation approach. So the master's only responsibility is to decide how many resources to offer to a specific application, which in Mesos terminology is called a framework. The framework itself handles its own micromanaging.
So the scheduling is actually delegated.
It is the two-level scheduling model. This is really the architectural breakthrough here. Step 1, the master decides how many resources to offer a framework. Step 2, the framework reviews that offer, decides which specific resources to accept, and then passes back a list of tasks it wants to execute on those resources.
Let me see if I can map this back to the restaurant.
Let's hear it.
Instead of you sitting at a table and ordering a highly specific customized meal from the kitchen, the waiter, which would be the Mesos master, right? The waiter just walks out from the kitchen carrying a massive tray of random appetizers. The waiter doesn't ask what you want. They just present the tray and say, here's what we have right now, some sliders, some fries, and a side salad.
Yeah.
You, acting as the framework, look at the tray. If you only need protein, you grab the sliders, you leave the fries and the salad, you hand the waiter your task instructions for those sliders, and then the waiter takes the remaining fries and salad to the next table to see if another framework wants them.
That captures the dynamic of resource offers perfectly. The master sends a concrete offer saying, Agent 1 currently have 4 CPUs and 4 gigs of RAM. The framework evaluates that and responds, I only need 2 CPUs and 1 gig of RAM for my current queue of tasks. I will accept that portion, and I reject the rest.
Wow, okay.
Yeah, and then the master launches those specific tasks on Agent 1, reclaims the leftover 2 CPUs and 3 gigs of RAM, and immediately offers them to a different framework.
But what happens if I'm a framework, I look at the tray, and literally none of it is what I need? Do I just reject the whole thing?
What's fascinating here is that rejection isn't just a byproduct of the system. It is actually the most powerful tool a framework possesses. Let's look at a practical scenario using Hadoop, where you need to process a massive data set. In distributed computing, moving terabytes of data across a network to a random server just to process it is incredibly slow.
Yeah, that makes sense.
It clogs up the network switches, it ruins performance. What you actually want is for your processing task to run on the exact same physical server where the data already lives. This concept is known as data locality.
But wait, because the master is just a thin layer, it doesn't track where your specific Hadoop data is stored, right?
Right.
It only knows about raw CPUs and RAM. So how can the framework possibly achieve data locality if the master doesn't even know where the data is?
By using rejection.
Oh.
Yeah, the framework evaluates the incoming resource offer. If the offer comes from an agent that does not hold the required data, the framework simply rejects it. It utilizes a policy called delay scheduling. Essentially, it waits.
Just waits.
Exactly. Because tasks are constantly finishing across a massive cluster, new resource offers are generated and sent out rapidly. The framework waits a short amount of time until the master randomly offers resources from the precise agent node that already holds the data. Once that specific offer arrives, the framework accepts it.
It just sits at the table rejecting trays until the waiter accidentally brings the exact tray it wanted all along.
Yes. And the data from the Berkeley researchers prove that this incredibly simple mechanism, just rejecting offers and waiting, yields nearly optimal data locality without the master ever needing to manage the underlying data architecture.
That is so smart, but I feel like this introduces a major friction point.
What's that?
Well, what happens when every framework in the data center is starving and they all want resources at the same time? You might have like a long-running web service and a massive batch processing data job fighting over the same pool of available servers. How does the master decide which table gets the tray of appetizers first?
So to solve the fairness problem, Mesos introduces a theoretical algorithm called dominant resource fairness, or DRF. The system has to look at the different types of resources like CPU, memory, and disk space and identify each framework's dominant share.
Can you break down the math on dominant share? Like, how was that calculated?
Sure. Let's assume your total cluster capacity is 100 CPUs and 100 gigabytes of RAM. Framework A runs tasks that require heavy computation. It might currently be using 10% of the total CPU in the cluster, but only 2% of the total RAM.
Okay.
Therefore, its dominant resource is CPU, and its dominant share is 10%. Mesos is designed to mathematically equalize these dominant shares across all active frameworks.
Gotcha.
So if Framework B is highly memory-intensive and is currently using 5% of the total RAM, the master will prioritize giving the next resource offer to Framework B. It always tries to offer resources to the framework with the lowest dominant share first, because 5% is lower than 10%.
So the master is constantly weighing the scales, trying to ensure everyone gets a mathematically fair slice of the total infrastructure based on whatever specific resource they need the most.
In theory, yes.
But
But theory and reality are rarely identical in distributed systems. When researchers from SUNY Binghamton tested this DRF theory in a real Mesos environment, the math broke down significantly.
oh no.
Yeah, they set up different frameworks, including Apache Aurora, Marathon, and their own custom framework called Scylla, and had them actively compete for resources.
What happened when the theory hit the real world?
Because the decentralized two-level scheduling model gives frameworks total autonomy to accept, reject, or hold on to offers, the Binghamton tests revealed that frameworks can unintentionally game the DRF system. When they ran a test with Scylla and Marathon competing for identical resources, Marathon ended up hoarding those resources.
Really?
The data showed that Marathon dropped Scylla's fair share of the cluster by 38%.
38%, that is a huge margin.
It is. And it got worse depending on the frameworks used. When they ran Scylla against Aurora, Scylla aggressively grabbed so much capacity early on that Aurora was starved by 67%.
Oh my gosh.
Aurora essentially had to sit idle, waiting until Scylla completely finished its jobs before it could launch meaningful tasks.
How does a framework mechanically hoard resources like that? If the master is controlling the offers, how is Marathon or Scylla manipulating the system to starve the others?
It comes down to how the framework handles the offer once it receives it. A framework can simply hold on to an offer while its internal queue of tasks builds up, waiting to see if it can make a more optimal scheduling decision later.
Taking it back to the restaurant, it's like a table grabbing the appetizer tray from the waiter, but instead of taking the food or handing the tray back, they just place it on their table and stare at it while they debate what to eat.
Exactly.
Meanwhile, every other table in the restaurant is starving because the waiter doesn't have the tray to offer to anyone else.
That is the exact mechanism of the starvation. The master offered the resources fairly, but the framework's internal behavior broke the system's overall efficiency. This highlights a crucial reality of Apache Mesos, which is that fairness is not an automatic out-of-the-box feature.
Right.
The master provides the mathematical mechanism for fairness through DRF, but the individual framework configurations dictate the actual outcome.
So if I am a cluster administrator responsible for keeping this data center running smoothly, how do I stop that hoarding? Based on the Binghamton research, what is the best practice use case for tuning the system?
The best practice requires active, customized tuning by the human administrators. You have to adjust specific attributes based on the real-world behaviors of the tasks your company is actually running. You mentioned the table holding the appetizer tray. To fix that, administrators must tune the offer holding period.
What does that do?
This places a strict timeout limit on how long a framework can sit on a resource offer before it is forced to return it to the master.
So you give them a time limit, make a decision, or the waiter takes the tray back. Exactly.
What else needs to be tuned?
Another vital attribute is refusal seconds. When a framework rejects an offer because it doesn't match its needs, like waiting for data locality, Mesos puts that specific agent on a filter list for a set duration. This means the master won't offer those same resources to that framework again immediately.
Oh, I see.
Yeah, if you don't tune this timeout correctly, the system gets bogged down in an endless loop of the master offering a tray, the framework rejecting it, and the master immediately offering the exact same tray again milliseconds later.
The research also highlighted task arrival rates as a problem area, right?
Yes. A framework that processes its internal queue and requests tasks at a highly rapid rate will naturally consume resources faster than a slower, more deliberate framework, entirely skewing the DRF balance. Administrators have to monitor and potentially throttle these arrival rates. Furthermore, the scheduling policy within the framework itself is critical. The Binghamton team demonstrated that by configuring the Scylla framework to use a bin packing scheduling policy, they drastically improved fairness. Wait, what does bin packing do differently?
Instead of just taking the first resource that loosely fits a task, a bin packing algorithm carefully calculates how to cram as many tasks as possible into a single resource offer, leaving very little unused free space.
Oh, like literally packing a bin as tight as possible.
Right. By tuning all these parameters, implementing strict holding periods, managing refusal seconds, and using bin packing, the researchers reduce the unfair resource allocation from that massive 38% down to just 3%.
3%. That is an incredible optimization. It shows the architecture is sound, provided the engineers operating it understand the mathematical interplay between the master and the frameworks.
Exactly. The human element of tuning is mandatory.
This brings up a critical vulnerability, though. We are talking about a finely tuned system where 50,000 servers are acting as a single computer. Resources are being offered, perfectly bin-packed and monitored. But this entire symphony relies on the master daemon acting as the central coordinator.
It does.
So if the single physical server running the master daemon suffers hardware failure and dies, does the entire data center go down with it?
In a naive implementation, a centralized master would absolutely be a catastrophic single point of failure. But Mesos prevents this by utilizing a highly robust, high availability, or HA mode. They do not rely on just one master daemon. They operate on a quorum system.
ZooKeeper is usually brought up here. I've heard it described as the traffic cop for distributed systems.
Traffic cop is a common phrase, but it doesn't quite capture the mechanism. It's more accurate to think of ZooKeeper as a board of directors taking a constant roll call.
Okay.
In HA mode, you have one active master designated as the leader, but you also have several backup masters running simultaneously, usually in a small group of 3 or 5. All the masters, agents, and frameworks constantly ping the ZooKeeper board of directors to verify who the current leader is.
Okay, so if the physical server running the leading master suddenly catches fire, what is the exact sequence of events to prevent a data center outage?
The moment the leader dies, ZooKeeper detects the disconnection during its roll call. The backup masters are alerted, and they immediately use ZooKeeper's election algorithm to vote among themselves. A new leader is promoted almost instantly.
But wait, the old master just burned down. Didn't it take the entire memory of the cluster with it? Like all the knowledge of which framework is using which CPU on which of the 50,000 servers?
This reveals another brilliant design choice by the Berkeley team. The master is designed with what they call a soft state.
Meaning it doesn't write its memory to a permanent hard drive.
Right. Saving the entire state of a 50,000 node data center to disk constantly would be incredibly slow, and it risks data corruption during a sudden crash. Instead, the master's knowledge is ephemeral. It only lives in active memory.
So it's just gone.
It's gone. When the new leader is elected by the board, it wakes up with essentially complete amnesia. It has no idea what tasks are running or what resources are available.
How can it lead if it doesn't know anything?
Because every agent and framework in the cluster is also constantly checking in with ZooKeeper. As soon as the election happens, ZooKeeper notifies all 50,000 agents of the new leader's address.
Oh, wow.
The agents immediately connect to the new leader and report their current status. They say, "I am Agent 1, and here are the specific tasks I am currently running for Hadoop." The new master just reconstructs its entire map of the data center on the fly based on those incoming reports.
That is incredibly resilient. And because of that soft state, the tasks actually running on the servers, like the Hadoop jobs, the web services, they never stop executing, do they?
They continue, completely uninterrupted. The only disruption is a brief pause in launching new tasks while the new master reconstructs its operational map.
What happens in a network partition scenario? Say an agent daemon loses its connection to ZooKeeper due to a faulty switch, but the master is still fine.
If an agent disconnects from ZooKeeper and cannot verify the current roll call, it enters a strict self-preservation mode. It actively ignores any new messages it receives from any master daemon.
It just completely stops listening to orders.
Yeah, it is a vital security measure against the zombie master problem.
The zombie master.
Right. Imagine the old leader master was disconnected from the network, but it didn't crash. A new leader was elected, but the old leader still thinks it's in charge. If the agent listened to that zombie master, it might execute rogue commands and corrupt data. By ignoring everything until it can reconnect to ZooKeeper and verify the true leader, the agent protects the integrity of the cluster.
Wow, okay. We have unpacked the two-level scheduling, the complex reality of resource fairness, and the quorum system that keeps it all alive. Let's look at the historical impact of this architecture. Looking at the Wikipedia history, the companies that adopted Mesos early on are the ones that really define the modern internet.
The adoption curve was rapid, primarily because companies were hitting the exact scaling walls Mesos was built to demolish.
Twitter's the most famous example. Back in 2010, they were struggling with constant crashes, like the infamous fail whale era, where their static servers just couldn't handle the user load. The creator of Mesos, Benjamin Heidman, presented the architecture to Twitter engineers. They adopted it, built their own custom framework called Apache Aurora on top of it, and used it to scale seamlessly to tens of thousands of servers.
Yeah, and Airbnb is another excellent case study. They used Mesos to manage their vast data processing infrastructure. They were able to run massive Hadoop batch jobs and real-time Apache Spark Analytics jobs simultaneously on the exact same physical cluster, achieving that high utilization the Berkeley researchers originally aimed for.
And eBay utilized it to solve a completely different problem. They used Mesos to create custom, private, continuous integration instances for their developers. Continuous integration is the process where developers constantly merge their new code changes into a central repository to test if anything breaks. eBay used Mesos to spin up these testing environments dynamically for every single developer. And then there is Apple. In 2015, they announced that the entire backend of Siri had been rebuilt on a custom Mesos framework they called Jarvis.
If we connect this to the bigger picture, that legacy cannot be overstated. Mesos proved definitively that a sprawling, heterogeneous data center could be operated as a single, flexible computer. It fundamentally shifted the industry away from static partitioning and laid the architectural groundwork for the entire modern era of container orchestration and cloud computing.
Which makes the end of the story so fascinating. Despite powering Twitter, Airbnb, and the back end of Apple's Siri, as of August 2025, the Apache Software Foundation officially retired the Mesos project. By October 2025, it was moved into the Apache Attic. Active development has completely ceased.
Yeah, technology evolves relentlessly. The solutions of one decade become the legacy systems of the next.
It leaves me with a provocative thought. If we look back at the original 2010 Berkeley paper, the creators explicitly hypothesized that by building this thin, unified operating system, specialized frameworks would be free to evolve and thrive. Because software developers no longer had to worry about building complex cluster management systems from scratch, they could just focus on building incredibly smart frameworks like Apache Spark, which was actually born alongside Mesos.
Right. The goal was to remove the infrastructural burden so 1,000 different frameworks could bloom.
So, did Mesos succeed too well? Did the massive success of the very frameworks it birthed the tools that eventually learned how to perfectly orchestrate containers and manage their own data environments outgrow the need for the underlying platform itself? Did Apache Mesos essentially engineer its own obsolescence by teaching the entire tech world how to build better, more specialized orchestration tools?
It's a great question. It suggests that Mesos didn't fail at all, rather. It completed its mission so thoroughly that its fundamental DNA was absorbed into the next generation of cloud infrastructure.
The restaurant learned how to run the kitchen so efficiently that they eventually realized they didn't need the waiter carrying the tray anymore. And that is a deep dive into Apache Mesos.